Next presenter is Abdul Azami from Rajshahi University, Bangladesh. And the paper title is TIG-UNet, a thresholded input-guided modified TIG-UNet for separating lung region in chest X-rays. Sir, I request you to please start with your presentation.
Yeah, please let me share my screen.
Yes.
Am I visible?
Yes.
Okay. Hello everyone. This is Abdul Jami from Russia University of Engineering and Technology, Bangladesh. I am happy to be able to present my study on TIG-UNet++, a thresholded input-guided modified UNet++ for separating lung region in chest X-rays. I was co-authored by these wonderful persons, Shadman Soban, Muhyiddin Ahmed, and Rakibul Islam. These are the outline of my today's presentation. Lung diseases like COPD, lung cancer, tuberculosis, pneumonia, and many more, they are the global health concern now. According to WHO, respiratory illness accounted for 3 of the top 10 causes of death in 2019, killing more than 8 million people per year. And you know that chest X-ray is widely used by the doctors and the radiologists to identify these lung diseases. And nowadays, AI-based chest X-ray classification is a hot topic in today's research field. And accurate lung segmentation can help for more robust classifications by allowing researchers to focus on the relevant part of the chest X-rays only. But this process is actually not very easy. Varying lung shapes, sizes, and overlapping organs makes this process difficult even for the experienced radiologist to segment lung regions. We figured out that the thresholded image almost roughly outlines the lung region in a chest X-ray. You can see here in the figure that the black pixels of the thresholded image actually roughly outlining the boundaries of the lung. You can compare it with the mask provided at the right side. There is pretty good similarity between them. So we got an idea to utilize this thresholded image as well as the original chest X-ray for better segmentation result. Various methods has been proposed by various researchers that includes thresholding, region growing, active control models, or recently machine learning approaches, and CNNs are actually best among them. And UNet is a very famous architecture for segmentation, especially medical imaging. And UNet++ is a modification of that standard UNet. It has more nested, dense skip connections and additional convolutional layers to refine features more perfectly. These are the literatures that we reviewed before getting into this study. Almost all of them used CNN based methods. Some of them used custom units. Some applied some attention mechanisms. Even some applied their custom encoder decoder based models. Even some used also GAN based method, generative adversarial networks. All of them have some limitations, like GAN can sometimes generate synthetic images, but we can actually ignore their limitations because all of them achieved very competitive and satisfactory scores. So our goal was to improve their segmentation scores little bit more. These are the datasets that we utilized: the Shenzhen, Montgomery, and the JSRT dataset. These are the pre-processing steps. First, we applied Clahy with clip size 2, and then this image was resized to 224 by 224, and it was taken as the original input. Then this image was at Orsus thresholding was applied to it, and we get the thresholded image from it. And I should tell you that our model actually have two inputs, and these are those two inputs. Here you can see our TIG-UNet++ architecture. That is what we proposed here. This architecture is pretty similar to the UNet++ L4 architecture with some minor modifications. The major modification is at the inputs. You can see a threshold image here. It was passed lately to that network, not at the beginning or not at the end. Why so? I will explain this later. For generalized training, we had to apply real-time data augmentation techniques. We applied random rotations up to 15 degrees and random scaling up to 0.8 to 1.2. These are the evaluation metrics we used to evaluate our model's performance: dice coefficient, Jaccard index, accuracy, and the AUC. Here are the equations, you may check them. We used dice loss as the loss function. We applied 5-fold cross-validation technique with each fold having 100 epochs. Batch size was kept 16 and 80-20 test and split, train test split was done. Hyperparameters training is pretty crucial for training deep neural networks, especially for us. We set the initial learning rate to 0.0001 and minimum threshold was 10 inverse 7. We reduced the learning rate on plateau after 15 epochs by a factor of 0.2. Early stopping was set up with on validation dice with patience of 20 epochs, and the best models were saved on base validation dice scores. Here you can see the scores of our TIG-UNet++ model across different data sets, and you can clearly see that our model performed really well on almost all the data sets, and this proves the generalized behavior of our model on diverse data sets. Here is a comparison of our TIG-UNet++ with the traditional UNet++ architecture, and you can see that our TIG-UNet++ achieved better performance than the UNet++ architecture in all the data sets shown here, and this actually proves the effectiveness of the thresholded image passed lately to the UNet++ architecture. This is the comparison of our model with other recent works, and you can see that our model outperformed other state-of-the-art works on Montgomery and the combined dataset. Combined dataset means the combination of Montgomery, Shenzhen, and the JSRT dataset, and it also achieved a competitive score on the JSRT dataset as well. Here you can see some predicted mass of our model, and you can compare them with the original mask, and you can clearly see that these two images are pretty close to each other. Well, now let's talk about why our approach worked better. First of all, due to the dual input strategy, the way we utilize the original chest X-ray and the thresholded image to improve the lung boundary detection, especially for the disease affected cases. As you I should tell you that Shenzhen and the Montgomery dataset contains several disease affected cases like tuberculosis, and obviously the UNet++ architecture and the use of the thresholded image. And the most important is that the late introduction of the threshold image. We you know that thresholding an image will remove most of the important most of the features of the image. So for better generalization, the original image was given most priority.
Hello?
So
So sorry for the interruption, but we are past the presentation time. Can we please conclude
yeah,
it?
I'm almost at the end. So we
Yes.
actually keep the less impact than the original image for the threshold image. So in conclusion, TIG-UNet++ advances the lung segmentation, and it outperforms several state-of-the-art models on Montgomery, JSRT, and Shenzhen datasets. We propose future works to extend this methodology to other medical imaging tasks like lesion segmentation and optimize efficiency for broader applications. Researchers may focus on making the model more lightweight, or they may add attention mechanisms as well. Here are the references. Thank you so much. That was all from me, and questions are appreciated. Thank you.
Can you go to results table?
Yeah. This one or this one?
Yes, yes. So what is the size of data sets that you have considered?
Okay, let me go to the slide. Here is the size of the datasets.
And the all images are in like good resolution, or you have to
Yeah,
do any.
they are at very good resolution, and but I resized them to a lower resolution like 224 to 224 for that was actually enough for me actually to segment the lung region.
And how did you store these images?
It was in the PNG formats, and for my training, I stored them in a .npy format, NumPy
Okay.
format.
And what do you mean by combined? So it is the combination of like
All
from
the
both the
data
data
sets,
sets.
yeah, all the data sets.
Okay. Thank you. Siddhi, over to you.